tool that machine up. Every time I tool one up with 73 stations, I swear, I mean, somebody's going to take the tools out on the other side. I mean, you just keep on going, and there's no end to it. So you got 110, that's a lot. How much fill you can have on the TABR press is all regarding your application, what you need to do, what you want to do, how big of a TABR you can make on the TABR press. What is the maximum tonnage? How much force you can put on there to make your tablet? How fast does it go? How many compression rolls you got, meaning you have pre-compression, main compression, and what kind of feeder you have. That's basically what you look for in the TABR press. Now here's a very simple TABR press. And again, when I'm saying they all work the same, I can walk you through this one. It starts over here where you start filling the powder into the die. So you have the feeder. The lower punch is going to get pulled down into the fill cam. The powder is filled into the die. It goes into a weight adjustment cam where you push some of the materials back. Then it goes into the compression. The tablet is formed. Then it goes into the ejection station. The tablet is ejected. So this is a very, very simple machine. You fill, you adjust the weight, you compress, and you eject. So there's no pre-compression. It's a very simple machine, but there's many of them out there, and it's making tablets. No problems with that. A top view, here's your arrow of rotation, so this one is going counterclockwise. And the start of the cycle is here. This is where you fill the powder into the dies. You scrape some powder off, and we're going to go in detail. I'll show you that. This one has a pre-compression. I'm going to explain to you guys later on what the pre-compression should be for. You have the main compression to make the final tablet coming around, and you have the ejection, and the tablets are taken off. So this one, compared to the previous one, just has a pre-compression. So you have a pre-compression and then a main compression. Now, if you do have a double-sided press, meaning of making tablets on one side and the other side, two hoppers, the powder actually is recirculated as well as on a single-sided press. But this view is on a double-sided press. So this colored powder here is showing you how the powder on the TABR press actually goes. Now in this one, we have a clockwise rotation. So we're going to start here with filling material into the die. We're scraping it off, and you can see how the material is scraped off towards the back of the die table. And it will go around and gets picked up on the other side on the feeder and is recirculated. Now in the single-sided TABR press is the same way. It just goes around all the way and gets picked up from the same feeder. So you recirculate the powder you scraped off towards the back of a die table. I think it's your computer, Mr. Mike. Mine goes.
It's going the right direction.
Is it? Anywho, that's a nice animation to explain what happened in the machine. So that is one side of a machine, or it is on a single side. It's a complete machine. Again, we start over here. You see running direction is going this way. So this is where the tablets are ejected. So your process is starting over here. You got the feeder, so you can see how the lower punch is pulled down and allows the powder to be filled into the die. Now I'm basically looking for four things to get the powder into the die. And I had a drink last night, so I don't remember. So I need your help. What do you think it is? How do we get the powder into the die? 4 things. Huh? Magic? It is all magic. I'll help you. First one is a feeder, right? I need to have some kind of a feeder to get the powder in there. So it could be a forced feeder, which has actually paddle wheels in there, turning around, getting the powder in there. It could be an open feed frame where it's just a gravity feed, where the powder just flows and goes into the die. So we got 1, missing 3. You were in the other class, so you're not allowed to speak. Okay. So he was saying vacuum from the lower punches. I don't have vacuum there. This is one of the things. I'm having a lower punch here, and I'm having a die. This is one of the things a lot of people don't pay attention to. And that's a very, very important function. If I insert the lower punch and I close the whole of the die with my thumb, and I pull out the punch, what I should hear is this. And that's what you're talking about is the vacuum, right? So while the punch is pulled down in the fill cam, at this point, it's a really rapid move. You go in the fill cam and the punch is pulled down. The vacuum generated by the punch tip inside the die is actually sucking the powder into the die. So if you got punches that were worn out on the punch tip, you got dies that are worn out on the inside diameter, you're going to have problems. Very important function. Needs to do that. Easy to check. Every time you tool the machine up, when you put the punches in, do this. If you hear the sound, you're good. If you don't hear the sound, you're going to have a problem. So that was number 2. We're missing 2. Anybody has overhead feeding? How you get the powder to the tower press? You got bins on top where the powder comes through? So that's called gravity, right? Gravity, or the static pressure of the material. So if you got a bin on the 2nd floor and you open it up and the powder flows onto the tower press, you have a static pressure on that material pressing onto the tower press. So as you go along and you're running out of powder, it's going to get less and less. So one more. The other thing, and we already talked about that's a fill cam. So you have to have the right size of a fill cam. The fill cam will determine how much powder you're going to put in the die. You need to have a good set of tooling to have the assistance of that vacuum inside the die to suck the powder in. You have to have a constant flow of your granulation going to the tower press. And then you can make a tablet. Now, how much time you have to do all this? Remember what Mike was saying yesterday, on an average, a tower press runs how fast? 50 per second, right? 3,000 tabs a minute. Now that is on a double-sided press. It's 25 on the right side and 25 on the left side. Now 25 tabs a second. Anything you have to do in the tower press, you get about that much time. We're not talking about a second. We're not talking 2 seconds. We're talking about milliseconds. So if I want to fill the powder in the die, that has to be completed like that. Anything else on the tower press, to make the tablet, everything has to be done like that. That's all the time you have to do. Let me go to the next slide here. So if you look at a inside of a tower press and you look at the die table or the turret, you have basically 3 sections on there. You have the upper section where the upper punch is inserted. You have the actual die table where the dies are inserted, and you get the lower section where the punches are inserted, the lower punches. Now, a lot of times you see damage on here, on the die table. Any damage on the die table is a poor setup. I mean, if you don't set the machine up right, you're going to have a contact metal to metal and you make a damage on the die table. That should be a nice and shiny surface, like you can see in here. There should be no lines on it, no damage. But I think any company I go to, you're going to see some marks on there and some scratches on there. The die table is made out of cast iron. So what is your opinion about what's harder? Is the tooling harder or is the die table harder? The tooling, right? Correct. The tooling is harder than the die table. So if I'm working in the TaberPress and I'm tooling up the machine and I drop a die on the edge on top of the die table, I can damage the die table. So it's very important that you handle it correctly. Now, another thing about tooling is, what's your opinion when tooling gets damaged? Where does it happen? On the tip, yep, see a lot of damage on the tip. But when does it happen? When you make your tablets? What are you saying? Outside the machine? Yeah. 90% of damaged tooling are coming from handling the tooling. It's not done in your process making a tablet. It's done during taking the punches out of the machine and throwing it in a bucket. I've seen that. All the dies just, you know, the operator takes a die out here, and he had a bucket with cleaning solution there, and he just goes bloop. So if you do that, you make a damage on the die. Let's say you have a little burr on the side here. What happens in the machine when you put the die back in? It won't go in. And solution to get it in usually is to get a bigger hammer. If you do that, you have a damaged die bore. So the dies, and they're sharp too and bleeding. The dies are very tight in tolerance to the die socket in the die table. And it needs to be in order to align the punches correctly. Because the upper punch is actually going out of the die, running through the cam track, and coming back into the die. And it needs to be aligned properly. If not, you're going to have damage around the punch tip. And if you got nice shaped tooling like hexagons and all kinds of funny shapes, they're very expensive. So you don't want to damage your tooling. So a damaged die will damage the bore, will damage your tooling. It's like a vicious circle going around. Another view of a simple TaberPress. Again, here you got your lower punch. You can see where the cycle just ended, where the tablet is coming out. So this is where we start. We're going into the fill cam. We're pulling the punch down. We're allowing the powder to go into the die. We're going onto the weight cam. We're pushing some material back. We have a scraper here, scraping material off. And then we compress the tablet and we eject the tablet. Simple machine. Now the TaberPress has no idea about the weight. It doesn't weigh the powder going in there. All the TaberPress knows is volume. So how much powder in volume I'm going to put inside the die. And that, in effect, will be your tablet weight. But the TaberPress doesn't know weights. So what kind of parameters to look for a tablet? We're looking for the weight, for the thickness, the hardness, the shape, friability, appearance, and content uniformity. What was content uniformity again? Anyone? Particle size, it's important to get the right content uniformity. That's one of the things I forgot last night. So what's content uniformity? Right. The content uniformity is telling you that you have, if your content uniformity is correct, that you have the same amount of ingredients in every single tablet you make. Very important. So I already gave it away. So how's a tablet formed? It comes through a hopper into a feeder. The feeder puts it in the die. There's a weight adjustment cam. We're scraping something off. We're going to compress the tablet and we eject the tablet. That's how easy it is to make a tablet. Sounds very easy. So what do we have to have in order to run the tablet press successful? One is flow, and Mike was talking about that yesterday. If your material doesn't flow, you're going to have challenges to make a tablet. Needs to be able to compress, needs to be able to eject. So if you have all that, you will be able to make a good tablet. I hear the rain. Free-flowing granulation. Again, particle size distribution, uniform density. That gives you a good content uniformity, and that results in a good flow. So I want to spend a little bit more time in detail on the 7 major steps how to make a tablet. Step number 1 is pulling down the punches in the fill cam. Step number 2 is the overfill below the feeder. Why do I want to have an overfill? Why do I need to have an overfill? Any idea? Help me out. That's a good idea. The other thing is, how much time do I have to do it? That much. So when I do that, what do I have in the die when I just pull the die down and get the powder in there? Is it just powder, or is there something else in there? Air, right? I have a very inconsistent amount of fill at that point. I'm trying to do the best in the time I have just to pull some powder in there, but there might be more air, less air, more powder, really don't know. So the overfill function is, first I have to put too much in there, and then I have to push material back. The remaining part in the die, that becomes your tablet weight. A lot of the times we're getting called for problems with weight variations on the tablet press. That is where you have to look first. It's the relation between how much you're filling into the fill cam and how much of that you actually use in your weight adjustment. So if you cannot push any material back, your weight variation is going to be sky high. If you have a good process where you overfill and you push some material back, you will have good weights. Now somebody can say, what I'm going to do, I put a lot of material in there and I always push a lot of material back. That should give me the best weight I ever had. Is that true? Not really. If you put too much material in there and you try to push too much material back, it has to go somewhere. And the machine is not designed to take that much material to go back. So you're going to see material build up behind the feeder. You have a lot of material loss. You see it coming off the die tables, building up on the surface. So if you fill too much and try to push too much back, that's not a good idea either. So you have to find the optimum on fill versus how much you use from the fill. Establishing the weights, that's done by the scraper. So again, if you overfill, that's happening in the fill cam. The majority of that overfill is pushed back underneath that feeder. So it actually is going back in the feeder. And a little bit, the pushback action is actually done by the scraper. Scraper is either a metal, stainless steel, knife blade, which sits on top of a die table, and scraping material off. At that point, you're done with making your weights in the tower press. That's it. Nothing else you can do. Containment and tail over die. Pre-main ejection. Let me get to the next picture so I can show you a little better. We're talking about this part here, the containment or tail over die. That is a cover sitting above the dies before the punch is entering into the dies. Another very, very important function on that one is, you see there is a little gap here. After you're done scraping it off, the lower punch is actually pulled down just a little bit. And if you buy parts from other than the OEM, they sometimes forget to put that little pull down in there because it costs more money to do that. If I have my coffee cup full with coffee all the way to the top and I do this, what happens? Well, he's going to be wet. So, since the die table is turning around pretty fast, you need to pull the powder down a little bit to avoid that you lose powder in that little space behind that cover, the tail over die, and where the punch is coming into the die. If you don't have that, you're going to lose your powder right there. So if my cup is like full to here, I can do all this and you're not getting wet. Of the cover? Touching? No, it's usually it's Delron. It's some kind of a plastic. The only metal part, either brass or stainless steel or other metals, is your scraper. And again, the scraper is a wear part, and we talked about yesterday that metal actually evaporates. I mean, it's wearing, right? You have to change, it's a wear part, you have to change the scraper once in a while. But when people ask, where's the metal going to go? It's going somewhere. And then the easiest way to fix it is to change your label claim on the bottle and say, including iron. You're safe. Right? Don't tell that to the FDA. They won't go for that. I hear you. Okay, so after I'm done filling the powder in, overfilling it, pushing some back, scraping it off, covering it up, making sure I don't lose anything, I have a pre-compression. Now, pre-compression is not there to make a final tablet. The pre-compression is there to evacuate the air. But you still have a mixture of powder and air. And I got a better picture coming later on to show you what I mean. So pre-compression basically makes a soft tablet. That's all it is for. And it allows the air to get out of the die. One difference between the upper punch and the lower punch is the tolerance of the tip. The tolerance of the lower punch, you can see, is very tight because you got the vacuum going on. If I use an upper punch and do the same, I won't have the same effect because the upper punch is smaller in diameter. And the reason for that is it will allow the air to escape around that punch tip. Got a picture later on showing you how it could look if you have a problem on the pre-compression. So after you got the pre-compression, you form your final tablet on the main compression. The only thing left is to eject the tablet. Now we looked at a picture yesterday of an ejection cam, right? Ejection cam is nothing else than having a cam which goes down like this. Punch is coming from here and trying to push out the tablet. Now, whenever you look at a ejection cam coming off the machine, there's one particular thing is always the same. The wear of the ejection cam is like this. So there's a point in the beginning where there's more wear, and then there's a normal wear. Any idea why that is? I'm trying to make a tablet, so I fill a lot of powder in this little hole of a die, and I compress the tablet inside the die. It doesn't want to be there. It's stuck. It's stuck in there. If you don't have any lubricant in the powder, you won't be able to get that tablet out of the die, I guarantee you. I used crowbars that long and longer, and we couldn't get it out. The only way we got that one freed up was chiseling the tablet out of the die. So no lubricant, you won't get it out. Now, if you look at the force, force versus time, my ejection curve looks like this. First thing I have is I got this high peak of force, and the reason for that one is that I have to break the tablet loose. At that point, the tablet is stuck inside the die, it doesn't want to move. So if I come to the ejection cam and I try to push it out, first I have to break it loose. That's the point where you get the highest ejection force. That is the point where you have the biggest wear on your ejection cam. Totally normal. You know, we had pictures sent to us saying, there's something wrong with my machine, look at this cam. And we told them, no, that's okay. That's the way it is. Any questions to this before I go away from that? The scraper, how close it is? Yeah, that's what it is. Yeah, it is a knife. And if you look at the feather, I mean, you get different. The question is the shape of the bottom of the scraper, right? So you have one like it's shown on there. You got a real knife. If you look, you got the feather machines. If you look at them, you basically have a square scraper, and it has that little thing in the back here. So that one is actually touching the die table. There's a little wear in the back touching it. But the actual, it's like a knife doing that. It also should prevent any buildup on the die table. So if you have, you know, sticking problems, the scraper should make sure that nothing sticks to the die table. The scraper itself is spring-loaded, so it's actually pressing onto the die table. It's not just floating on there. It is loaded, pressing onto the die table. Yeah.
The scraper blade, to me, is the heart and soul of the whole thing. So I just want to, because I think the question is really good. I think that if we look at the die table, and we look at the three designs, the most common one, like Peter says, is what's up on the slide. Geometry is is this knife edge. I'm a lousy artist, as you've already learned, but I have a really sharp edge. The problem with the knife edge is that like Peter says, as this table's turning, as the die table's turning around, the blade is floating on the die table. That's the only thing that's actually scraping or touching the table. So we've got spring pressure downward on this blade, and so that blade is going to continue to wear. As it wears, it gets wider and wider and wider, right? You can see that because of that blade edge, it keeps getting wider. So as that blade gets wider and wider and wider, our ability to scrape off really precisely and cleanly gets worse and worse and worse. It's not as good. Okay? And so the blade, as it gets wider and wider and wider, doesn't, and so you leave a little product on top of the die table, and that's a potential for the materials or inaccurate weight control. The wider this blade gets, the worse your weight control becomes. Now, like Peter says, there's different designs. The Kikasui press that's right back there, those three presses back in the back, they actually use a blade design that's a little bit different. I kind of like it because this part of the blade stays the same. That's supposed to be equal there. And so the downward pressure, as this blade, even though it starts out wide, as it wears, it always stays the same until it wears completely out. So it's very uniform. So there are different types. I mean, I've used bronze blades. I've used Teflon blades. I've used plastic blades. The problem with non-metallic blades is that there's not really a non-metallic detector. There's no way to, if that breaks or fails, so the idea of a metal having a metal blade, if there is some major failure other than normal wear, you're going to detect that. You're going to be able to reject anything that comes off that blade, because really the blade is the only thing that's really touching that table. Its job is to make sure that you scraped off that table and you have the right amount of powder in the die each and every time. That's how you're going to get weights. That's the key to success on any press, is making sure. I mean, if you do one thing, if you learn one thing about tableting, if you're a supervisor or manager or anything, when you go back and look at this little press or you go back to your plant, one thing I'd like you to do is go look at your presses. And when you walk out there and you stand there, I want you to look behind the scraper blade and watch how clean the die table is. If the die table isn't really clean as a result of good scrape off, you do not have optimized weight control. So all the work you did with milling, blending, granulating, all rests on how good of a job the scraper blade does. Because if that scraper blade doesn't give you that proper volume of fill, then nothing else counts. Does that make sense?
Absolutely. Absolutely. Thank you.
I'm going to sit down now.
No, I'd like you to come on. Thanks. Yeah. Correct. Yes.
So it's because it's raining outside, I want to make sure everybody heard what he said. He said he's asking about the whole setup of the feeder and the die table and the scraper blade and everything. So typically the feed frame is set a little bit above the die table. Most machines, you look at these machines here, these Manistys and everything, there's clearance between the die table and the bottom of the feed frame that's roughly the thickness of a piece of paper in that notebook. The piece of paper in that notebook in front of you is about 3/1000ths of an inch. So that clearance is critical. We can't have the die table hitting the bottom of the feed frame, or we're going to have problems. We're going to have metal. So we need that clearance. If the clearance is too big, then the powder leaks, and we get big piles of powder off the press. We lose product. It affects our yields. So our objective is to get that feeder as close as possible without having leakage. So that's why we're setting the feed frame at 3/1000ths. So then the blade, so we've we've set that right. We overfilled the die. We used the blade to scrape the excess off to get the right weight. That's our proper tablet weight. The tail over die keeps, as Peter said, right, keeps the centrifugal force from allowing the powder to leave the die. So that's actually riding on the table. You don't see it on slower machines, older machines. You see it on newer, higher speed machines. Pre-compress, main compress, and get the tablet off the machine.
Thank you. So let's look at that graphic again here. So the first thing we're talking about is here, step number 1, pull down in the fill cam. So that's happening right here. You can see it how the punch is pulled down. Most important function on that fill cam is it needs to be big enough so you can overfill the die in the beginning. That's what you have to remember. The fill cam has to be big enough. So step number 2 is your overfill and the push back action into the feeder. So you're coming into the fill cam. At this point, the punch is at the lowest position. It gets the powder into the die. It goes up the weight adjustment cam, and it's pushing material back into the feeder. Boy, someone's mad with me. After the feeder, you have the scraper bar. So the scraper bar is scraping off the last little bit of material from the die. At that point, if it leaves that scraper bar, that's where you're done being able to change your weights. After that, the weights are done. Nothing you can do to change it. Use your tail over die, covering the dies. And you also can see that the punch here is pulled down just slightly to allow this little gap so you don't sling material out when it comes out behind that cover before the upper punch is going into the die. Then you got your pre-compression roll and your main compression roll where you make your final tablet. You go into the ejection where you eject the tablet. So, got ahead of myself here. Scraper, number 3. Get them all up here. So that's all 7 steps. Your scraper, your tail over die, step number 5, pre-compression, number 6, main compression, number 7 is ejection. One of the more common problems we see out there is when people tool the machine up and they insert the dies inside the die table in the socket, where do they have to sit? What's the most important thing on the die? It needs to be flush with the die table, right? Not below the die table, not above the die table. Flush. If you don't clean the socket where the die gets inserted correctly, you can have the die just sticking out a little bit. Now, what would that do? What would be your part affected by that? Scraper, right? So the scraper is going to wear out over the width of the die. And if you have only, buddy's mad with me. If you only have one die sticking up, it's going to wear the scraper plate and everything else going by are not scraped off correctly. So very important function to set the dies correctly that they are flush with the die table. The other question I have, what should be, if you look at the ejection point, where should the punch be as far? I'm screaming. I noticed, but I'm screaming. So ejection height, where should the punch be? A little bit above the die. And how to check that is, it's a calibrated fingernail. You just go over the die table and you feel that you can feel the punch tip. It should not stick out a lot. It just should be slightly above the die to make sure that the tablet is able to get out of the die. Yeah. Uh-huh. Okay, question was, the tablet press has a vacuum. The vacuum is usually around the die table, right? And where does the vacuum go? Probably in your house vacuum. The importance of it is to get rid of dust. And I have a picture in a minute, and if I can come back to your question at that time, it would be great. We'll talk a little bit about defects on tablets. You never seen that, right? Never, ever. One of the most common problems is capping. And capping is the tablets actually are separating on top. So the whole top cap is coming off. Reason for that is you can have air entrapment. So when you compress the tablet, all you have is the powder, and you also compress air. So when the tablet comes out of the die, it wants to expand a little bit, and that's where it caps. One of the safe bets I always do, my bet is that if you can get a tablet back into the die after it was ejected from a tablet press, I give you $100. I haven't paid any money yet. Every time the tablet comes out of the die, the tablet expands. So it gets larger. So you won't be able to get it back into the die. Punch penetration. What is the punch penetration? It's actually where you're going to compress the tablet inside the die. I can compress it on the upper part of the die, on top of the die. I can press a little lower in the die. That's your penetration depths. Got a picture on that coming up too. If you have a lot of fines in your material, Mike was talking about fines yesterday quite a bit. Fines are your enemy. So they can cause your capping problem. Poor blending. Poor blending is you don't have a uniform blend. So you got all the big particles in one section of your run, and you got all the fines in another section, and you have all kinds of problems. Overmilled feeder speed, tooling design, and tooling condition. I have a picture of that. Now, it also can come from your powders. I mean, there's powders out there, it's their nature. They cap. So if you don't, attack the powder itself and do something to the powder, either granulating it or doing a pre-blend to coat that powder, which has that nature of capping, then you continuously have problems. Poor binding, segregation on materials, and that could happen in blending, or it could happen on the tablet press. How can it happen on the tablet press? One of the biggest mistakes people make setting a tablet press up is, as fast as I run the feeder, as better I fill. Would that be a true statement? Right. I mean, you got two paddle wheels going in there, and all they're for is to supply enough material over the dies that it can be pulled into the dies. The paddle wheels inside your forced feeder are not actually pressing the material in the die. So if I run too fast, all it does, you have a mixing going on inside the feeder. And you can demix your powder. So the optimum speed of a feeder is always on the low side. You don't want to go that fast. You don't want to ruin all your work you did in granulating and blending it and then just ruin it in your feeder. Some more pictures of capping. The funny thing about capping is the best way to find out that you have a problem is from the operator when they check the hardness of a tablet. You check the hardness of a tablet, we're going to do it over there, the tablet should crack, should break. If they see during the hardness testing that it separates, the top cap comes up, and it's the same for lamination I'm going to talk in a minute about. If they see when they test the tablet for hardness that it laminates or the cap comes off, you know that you have a problem. Okay, so here, a lot of information. We're talking about the capping happens on the top part of the tablet. So this part actually comes off. If you get a tablet off the press where you have a problem with the lower side of the tablet, that's not capping. That's either lamination, sticking. Now here is the inside of a die. Here's your powder to be compressed into a tablet. You can see that there is a different diameter between the lower punch tip and the upper punch tip. So the upper punch tip is smaller. Reason for that again is to allow the air to escape while you compress the tablet. Very important function. May look like capping, seen that a lot. If you have a damaged tip on the upper punch, somebody dropped it, somebody accidentally compressed the upper and lower together, you can actually bend the side walls in. And then it will grab the top part of the tablet and just take it off. So you get the tablet off the press and say, oh, that's capping, and you troubleshoot it the normal way by looking at all kinds of settings in the machine, and the real reason is it is bad tooling. It could be multiple, but usually it's like, single events. Somebody drop. What do you do if you drop a punch? What I do, the first thing, I look around if everybody's seen it. I'll pick it back up and put it in the machine, right? Right. No, they are not stainless steel. No. There's different combination, like an S7, there's a D3. It's not stainless steel. Stainless steel won't be too brittle. It would break. Nope. Yeah, no, there is technology out there where you can coat your punch tip. I did something wrong last night. But majority is just an S7 or D3. That's what they usually use to make the punches. And it's not hardened extra on the tip or coated. So when does it occur? Capping can happen right away when the tablets come off the tablet press, or it can happen a week later or 2 weeks later. And like I said, hardness tester will tell you what can happen. Poor setup. I've seen machines. This is normally covered. And you're smiling. You ever seen that on your feta? Liar. Anyway, I've seen machines where they got like 25 kilograms of material out of that. People don't pay attention. The machine was not set up correctly. It was leaking really bad.
He asked a question about dust.
Coming to it. Didn't forget it yet. Fines are small dusty particles. Results in poor flow, poor compression, becomes airborne. So there's one of your need for dust collection. Requires more dwell time and is sensitive to overcompression. What does it mean, overcompression? If you look at I need to hurry up. If you got the force here, no, the hardness here, and the force over here, that doesn't work. Whoa. Ginglish. Officially Ginglish. If you look at if you increase the force, your hardness first will go linear. Your hardness will increase like that. Then it goes like this. And then it goes like that. So in the beginning, you apply the force to the powder to form your tablet, and your hardness of the tablet will go up on a linear base. Then you come to a point where it plateaus, where it just doesn't change anymore. And then it actually comes to a point where the tablet gets softer. Now, if you're at that point where the tablet gets softer, you overcompress the tablet. And you just have to picture like a sponge. If I compress a sponge and let it go, what happens? It's going to come to the same shape, right? So I just overcompress it, tablet relaxes, doesn't get any harder. So a lot of times you're attacking a problem on the tablet press saying, I got capping, I got hardness problems, not enough. The normal reaction is I need more force, and I just crank it up, and the tablets doesn't get any harder. They don't get harder because they overcompress. So we get calls and we say, okay, the first thing you need to do is back off on the compression force. The guy on the other side goes, I just told you I don't have enough hardness. I say, well, yeah. You use less force to get better hardness. And a lot of times that's what it is. Just a little graphic about the fines. Lamination. Now, lamination is where the tablet laminates in any area of the tablet. Any part of the tablet, it just has a lamination. They just come apart. And that's where particles are not locking together. They are not able to form a tablet and stick together. Talked about it. I need to hurry up a little bit here. Solution for lamination. Apply the correct force. Again, overcompression will result in all those little problems. Capping, lamination. Increase the dwell time. How can I increase dwell time on the machine? Slow down, right? Well, I was in charge of manufacturing, and if somebody tells me I need to slow your machine down, I didn't like it. But sometimes you have to do that. The punch lengths and check for wearings inside of the die. The dies are wearing out as you make tablets, so you can actually look on the inside of the die, and if they're worn out, you can see a wearing inside the die. So basically, the wearing makes the die larger on the inside, so you make a wider tablet and try to push it out through the bottleneck. And that's not going to work, so the tablet's going to laminate, falls apart. Oh, never seen that before. Sticking and picking. Usually comes from your material. A lack of lubrication, poorly blended lubricant. And that could be on both sides. It could be not enough blend time or too much blend time, like Mike was explaining yesterday. Heat and humidity. A lot of the materials you have to work with, they're heat sensitive. And whenever you run a tablet press, the tablet's coming off the machine, they're actually warm, they're hot. So over time, the machine will heat up, and suddenly you got this picking problem. because materials are melting. The moisture either in the environment, in the product, or in the process, dwell time again, and the cleaning practices in startup. So if you have a really dirty set of tooling and say it's going to clean itself anyway if I start the machine, you might have sticking problems. After the machine heats up, feed frame and compaction on the die table. You've probably seen that while the machine is running. Suddenly you have a build-up on the die table. Remember the pictures from yesterday? Same thing. I mean, this is where it comes from. That's where it starts. So a lot of times you have to deal on the compression machine with errors and mistakes made on the previous process. So if it's not done correctly in weighing or blending, you can have a problem resulting on the tower press. What to look for? You look for the buildup on the powders, either on the punch tip, either on the die table. Behind the scraper blade, like Mike was saying, if the scraper blade is wearing out and not doing the job anymore, suddenly you have a buildup on the die table. Look for powder leaks around the feed frame, easy to identify. And look for the adherence of the tablet, the powder to the tablet. Who ever had black specks? Anybody? You're brave. You're saying you had them? Everybody has black specks, right? Yeah. That's why we coat. That's right. Black specks come from either the material. So if you have a problem during milling and you burn some of the raw material, suddenly you got black particles coming from that process mixed in your powder. You're making a tablet and there's a black speck. It can come from materials inside the tower press, like the buildup around the punches. They are mixed with oil. They turn black. They fall down. You got a black speck. One important thing, whenever you have to deal with a defect of black specks, the only thing you have to do is not saying, most likely it came from the lubrication of the machine. Investigation closed. You get in trouble with that. You really have to identify what it was. So you have to take a little sample and prove scientifically that it is actually oil and powder. And the FDA knows that you're going to have black specks. So root causes: lubricant, cleaning, dust, densification, dust caps, defines, powder reactions. Usually comes from your machine setup. Look at the feed frame. The buildup around the punch tip, usually around the upper punch tip and the dust cap or oil cap.